In this video, I'm going to help you go through some work and energy calculations. This is part of topic 2.3 in the IB Physics Syllabus, so it's important for SL and HL students. Take a moment to read the success criteria for this video. I will assume that you already know how to use the equation work is force times distance, and that force and distance must be in the same direction. The same with conservation of energy. The energy can neither be created nor destroyed, only transferred or transformed from one form to another. I also would expect that you know how to calculate kinetic energy, 1/2 mv squared, and gravitational potential energy, mgh. Okay, so let's do one question where we're just looking and reminding ourselves about these forces. We've got a box on an incline, and you see we have a normal force, the force of friction, and weight. And because of how they've drawn friction, I can see that this block is sitting there, and it is either just sitting there or it's sliding down. But it's definitely not sliding or going up the hill because friction always opposes the motion. Now the weight, right, is the force due to gravity, and I could break that up into two components. The force due to gravity that's perpendicular to the surface, and the force that is due to gravity parallel to the surface. Remember, we can break up a force into any two perpendicular components, and we do it this way because now I only have to break up one, the force due to gravity, rather than breaking both the normal force and the friction force into both vertical and horizontal. Now, because it tells me that this is at rest, that means all forces are balanced. That's Newton's first law. If all forces are balanced on an object, it will travel at a constant speed, velocity actually. And in this case, my constant velocity is 0. So that means friction is going to equal the parallel component of the force due to gravity. It then also means that the normal force, as we're working perpendicular to the surface, is going to equal the perpendicular component of the force due to gravity. So one last thing to point out is when you break them into components, right, we're talking about thinking about our rectangle rule. This is the diagonal of our rectangle. That means this weight here is going to have a greater magnitude than either of its components, right? It's the hypotenuse of this triangle. So if we say the box is at rest, going back to the question, the net force acting on it is equal to, well, actually, we did all that work for nothing because the answer is going to be 0. It's at rest. It has a constant velocity of 0. Well, not really for nothing, because we need to make sure we understand this vector work for questions coming up. Okay, so let's use a question with conservation of energy, and for now, we're going to neglect friction. We have a roller coaster. It has a mass of 290 kilograms. It's going to start from rest here at the top, and it will acquire 3.13 times 10 to the 5 joules of kinetic energy as it gets down to the bottom here in 5.3 seconds. So we can then assume that at the beginning all it had was potential energy and it wasn't moving, and we converted all of that potential energy into kinetic. Okay, so now in terms of calculation, potential energy is going to then at the top equal the kinetic energy at the bottom. And potential energy, mgh. Kinetic energy, the equation is 1/2 mv squared, but we don't need that because we actually have the number of joules here, 3.13 times 10 to the power 5. I'm going to rearrange that for the height. Mass will be here on the bottom, 290, and g being 9.81 meters per second squared. Now, in this case, we don't have to worry about it being a negative sign because energy is a scalar, and that negative sign was determining its direction, telling us it was pointing down. So I'm going to pick up my calculator, and it gives me a value of 110 meters. I'm just going to write that in here and erase my working so I can calculate the next part. Okay, it wants to know what the speed of the roller coaster is at the bottom. So I need my equation for kinetic energy, 1/2 mv squared. And I'm going to move this around for v. So to get 1/2 to the other side, either I could divide by 1/2 or I can multiply both sides by 2. So 2ke, and get the m over to this side, it's going to be divided by, and that would give me v squared, but let's be a little bit lazy and just go right to the square root. So 2 times 3.13 times 10 to the 5 over my mass of 290. Pick up my calculator, and I get 46.5 meters per second. I'm just going to write that in here and erase my work so I can finish the question. Okay, calculate the magnitude of the average acceleration of the roller coaster as it descends to the bottom of the hill. So that is acceleration. So the first thing I need to realize is I'm going to have to use SUVAT. And we've got the time, 5.3. And earlier we suggested that the initial speed was 0, that it didn't have any kinetic energy at the top of the hill. I'm looking for acceleration. And so now I need to either get that distance or its speed at the bottom. Now, we actually did just calculate that speed at the bottom, 4.65 meters per second. So, and I just said 4.65, obviously 46.5. One of the things I want to caution about is trying to use the height as being 110 meters. We don't know it's going to be that. In fact, it better be a little bit longer because we're not going straight down. We're going down a hill. And so we don't actually know the distance we're traveling. We also shouldn't be expecting an acceleration of 9.81 because this isn't free fall. We're actually going down the actual track. So here we've got so far, but all these data we've been using so far. So what I need is an equation that has A, V, U, and T. And so I go to my data booklet. I love my data booklet. And I find the equation I'm looking for, V minus U over T. And we'll make this really nice and easy because this value is 0. So in fact, we're looking for 46.5 over 5.3. I'll pick up my calculator, and I get 8.8 meters per second squared. I've rounded it to two significant figures because that's all I had in my time value. Okay, example 3. A 10-kilogram child slides down a 30-meter long slide, inclined at 30 degrees to the horizontal. So that means along this distance, this is 30. We've got 30 degrees here. And a force of friction, remember that's parallel to the surface, is 35 newtons. Okay, so I just moved my diagram to the top so I have a place to write here. At the beginning, potential energy lost. So what we need to know then is for potential energy, we have mgh. I've got the mass, g is 9.81, but what I'm missing is the height. What I have right now is the distance along the slide. What I need is this one here. That's okay, we've got trigonometry, no problem. So compared to my 30 degrees, this side is opposite. And I know the hypotenuse. So that's going to be sine. Putting my values in, I will have 10 times 9.81 times 30 sine 30. I'll pick up my calculator, making sure my calculator is in degrees, and I get an answer of 1,471 joules. I have some extra significant figures right there. That should be rounded to two significant figures, because if you look here, this has 2, this has 2. So that should just be 1,500 joules. Now the next part, work done, is the force of friction times the distance. And if you remember, the force and distance have to be in the same direction. Or another way to think about it is, if we're working against force of friction, it was all along this surface. So we need to use that for our value of distance. So force of friction, it told us, was 35 times that distance of 30. I pick up my calculator and I get 1,050. And I'm just going to put those values in over here so I can erase this and have space to work. And if I round that to two significant figures, it would be 1,100. I'm just going to leave it as this for now, keeping an extra significant figure until the end. So now we're looking for the kinetic energy at the bottom of the slide. So let's think about what we had to begin with. At the beginning, at the very top, we had 1,500 joules of potential energy, of which 1,050 has gone to overcoming friction as we come down. So how much is left over? Well, that would be 450 joules. So what we're using here is our work energy theorem. So we have the amount of energy can't be created or destroyed, only transferred from one form to another. And when we do work to overcome friction, that's going to cause us to have heat created. And so that's where some of our energy has gone. Now that I have the kinetic energy at the bottom, I can use my equation. Kinetic energy is 1/2 mv squared, and then I'm going to move this around. V will be 2 kinetic energy over mass square root. I have taken my 1/2 to the other side by multiplying both sides by 2, divided to get the mass, and then take the square root. If I put those values in, 2 times 450 over the 10 kilograms, and I'm going to pick up my calculator, and I'm going to get 9.5 meters per second. Okay, and one more example here. I have a block weighing 40 newtons released from rest on an incline of 8 meters above the horizontal. So it tells us in this case 50 joules of the energy has been transferred to heat. What's the maximum kinetic energy? So if I had only potential energy to begin with, that's going to equal the work done to overcome friction plus whatever kinetic energy I have left at the bottom. Remember, this equation will depend on the situation. If I had a block going from the bottom and I was speeding along and it went up to the top and we said, how far can it go? How high can it go? Then that means the kinetic energy would equal the force, the work done to overcome the force of friction plus the potential energy. You need to actually create this equation due to the circumstances you find in the problem. It's not a one-size-fits-all. Now, if if I do this, I can rearrange and I can say then my kinetic energy will be that potential energy minus the work to overcome friction. So mgh minus, in this case, it told us it's 50. I don't have to calculate that, but I do have weight. M times G is 40 newtons. Remember, mass is measured in kilograms. The height, it said, was 8. I'll pick up my calculator, and I get 270 joules. Next, it says if the incline was 20 degrees, what is the coefficient of dynamic friction? So we know that the amount of work done to overcome friction was 50 joules. In order to do this, then, I'm going to need to know what the force was of friction and then also the distance it traveled. Now, the distance it traveled, let's do that first because it will be a little bit easier. This is 20 degrees here, so I would need to calculate this distance here. Now, 8 is going to be my value that is opposite the angle, and I'm looking for the hypotenuse. So in this case, I'm going to have opposite and hypotenuse, that's sine. So sine 20 will equal 8 over the actual distance I'm looking for. So the distance will be 8 over sine 20, which will equal, picking up my calculator, 23.4 meters. Okay, so I'm going to move some numbers around so that I have a place to work on the side. Our kinetic energy at the bottom was 270 joules, and so now I'm going to erase my work and work on the side. Okay, so our equation, work is force times distance, and in this case we're talking about the force of friction. If I put in my values, I have that we had 50 joules over our 23.4, which gives us, picking up my calculator, 2.14. But we're not quite done yet because it didn't ask me for the force of friction, it asked me for the coefficient of dynamic friction. And dynamic because it is moving down the hill. So if I look back to the equation for friction, mu Fn. Okay, Fn. We need to go back to this diagram for a second. We have force due to gravity pulling straight down. And we can break it up into its components, Fg perpendicular and Fg parallel. Now, yes, it's accelerating down the hill, but perpendicular to the hill, it's staying on that surface the entire time. So that means the forces are balanced in this direction, perpendicular to the surface. So that means that the normal force will equal Fg perpendicular. And in addition to that, we also know that this angle right here is going to be 20 degrees. I'll leave it to you to go through and check to see that yes, that really is 20 degrees. Now, my component here is going to be adjacent 20, so that means that this component is going to be Fg cos 20. I'm going to put that in my equation. So the force of friction was 2.14 newtons. Mu stays there. Force, that normal force is going to be Fg cos 20, and we know that mg is 40 newtons in this case. They gave us the weight, not the mass. And if I pick up my calculator, I will get 0.060. So not a lot of friction. Maybe it's something on snow or ice. Okay, so take a moment to read the success criteria one more time. I hope after this video and our examples that you'll be able to say yes to these success criteria.